All right. I think it's working. Yeah, thank you. That's a very generous introduction. Thank you. So today, I'm going to talk about small and practical AI models for CO2 reduction in buildings. But before I'm going to do that, I'm going to want to show you a picture, because this morning I had quite some nerves coming here. And I was on my bicycle and I saw this. And I looked at it and I thought, like, you know, let's not forget what it's really all about, what we're doing, right? I live in Groningen. I have to cycle this every day. It's beautiful. We live in Groningen and we develop technology. I love technology. But sometimes in the world as it is right now, with all the open AI stuff going on, at least in my opinion, it's quite overwhelming, right? In the past year, I followed the news lines and I saw this. I saw there's a new model. It has 7 billion to 65 billion parameters. I have here the GPT-3, 175 billion parameters, right? Google Bard, it updated, it gets bigger and bigger and bigger. So then I started looking at some other research. So I found this one, learning to play Minecraft. I thought, just to be nice, right? Just a little bit more easy. I started looking into the paper, and what they did, they trained for 9 days on 720 GPUs, right? But then I read further, because this was the pre-training. What they actually did, they trained on 56,000 CPUs for, what was it? 6 days, right? And then I was like, what's going on? That's so big, I can't even imagine it anymore. And this is another one. This one is about the Dolly. It also has billions of parameters, right? So why this talk? Well, basically, I'm not here to impress you, to blow you away about how many parameters we use, or how big it is, or how large we can scale it. No, I'm going to talk about how we apply small AI models. I want this to be accessible. I want it to feel like we also can do things with AI when they're small, right? So that's my goal of this talk. And first, yeah, this also, I inserted this. Who am I? It's also nice to say. I'm Bram de Wit. I'm the lead AI engineer at Advanced Climate System. I love to cycle. I already said it. NeoVim is my favorite text editor. Fight me. And I eat vegetables out of my own garden. They already said that as well. So that's just a bit about me. What I'm going to talk about today, I'm going to talk about 3 things. I'm going to explain a use case, just to give some business context. I'm going to talk about the AI solution that we used. It's a bit more about the model, but most importantly, I want to talk about how it was engineered, how we set up our ecosystem for small AI models within the company, all right? So the use case. I want to take a moment to look around. Who has it cold right now? Is there someone who thinks it's cold here? One person, nice. Who thinks it's too hot in here? Okay. Who thinks maybe, I don't know, the CO2 levels are too high? They feel like it's a bit, all right, yeah. Well, this is what the company where I work at is all about, basically. What we do is we regulate the climate systems within buildings. We connect them to the cloud and we basically control them with software. So what we do, we control the equipment, that's what it's called, and they are called the HVAC installations, heating, ventilating, and air conditioning. So what's that? We control these things. It's an air duct that regulates airflow. It's a ventilator, does basically the same thing. This is the one that's for water. You can turn on like the water, and then with the 3-way valve, and there are a lot more of the things. But they're all things we've all seen before, right? We've seen them on buildings and everything. Well, this is what we do. We control them. And we collect data from them. So we place sensors in it, we collect data every 10 seconds, and we basically collect data from them. So why should we even care? I thought it was nice to also explain that. That's because buildings use 30% of the energy of the world. So that's really a lot. And about 15%, half of like the 30%, so 50% of all the world energy is used by these equipments that I just showed you. So making improvements on how these equipments work really can have an impact in how much energy we use. And I think that's a relevant theme right now in the world. So that's the why care. The use cases. When we're not in a building, we don't want it to be heated. That's like an easy thing, right? So this is a very normal set point scheme. A set point is the desired temperature that you want your room to be, okay? So we see it's 15 degrees in the night, then at, I can do this, yeah. At 8 a.m. we see it jumps up, it becomes a bit warmer, and then at 16 it jumps down and the night begins, right? This is very, very standard. Are there any questions? Is this clear? If not, just raise your hand and I will just answer questions in the meantime, right? So this is a normal set point scheme. What happens is often this. The blue line is the inside temperature of a room. What we see, we preheat a room, so that's warm when people get there. But what we see is around this time, this is all energy we put in there. It's just electrical energy or gas or all that kind of stuff. But then around this point, the set point is reached, right? The room is warm enough. But what then happens is then the sun starts shining. It becomes warmer and everything, and the day starts. And what we then see is all this energy is added by the weather. Okay? This is all excess energy, and it basically means that the energy that we used here is sort of wasted. Not entirely, because we don't want it to be cold when we get there, but there's a trade-off here. All right? So the goal was refrain from heating a room when the weather will do so later. Constraint, it should not cost too much comfort. So we don't want people to come in at 10 degrees, but in 5 hours it's warm enough. No, that's not right. Okay? This was the use case. Everything still clear? Good. Next, the AI solution. So what did we do? Well, we built a model that predicts the difference in temperature of the room temperature given the weather forecast. And we do this on an hourly basis. It's not an extremely hard task. We built the data set, this is for small nuance, only when the HVAC system was turned off, because otherwise you get like mixed data of how much energy the weather is adding and how much energy we are adding, so we only do it when we don't activate the HVAC system. And the best performing model was a multi-layer perceptron. It was very simple, it was the best by far. We tried linear regression, just all the standard stuff, you guys know it. So this is how it looked, and a bit more information about it. We create an individual model for every room. This is something that I want to stress, because we don't have metadata about the room. We don't know how big it is, we don't know how well it is isolated, and we can collect this data, but this is very costly, so it's easier to create an individual model for every room. It has a roughly, it differs per room, but it has like a 0.1 degrees Celsius error. It has 9 inputs, and it has less than 1,000 parameters. It takes 5 minutes to train, and the model size is, I just checked in the break because I wanted to be sure, it's 7 kilobytes for one model. And that's including all the metadata and everything, and it's a zip file, including the model as well. So it's small, right? Now I want to talk about how we engineered it. How did we build it into our ecosystem? And for that I have to take you on a tour a bit on how our whole technical stack looked like. So we have a building, just like could be the forum, for example. What we do, we place a edge device there. This is called a smart base. We call it the smart base. And it's an edge device, we connect sensors to it, and that is connected to the cloud. How does that look? It communicates via an API, all right? Standard stuff. Behind the API, there are 2 databases. We have a MySQL database and an InfluxDB database. How many of you know InfluxDB? Oh, quite a lot. Okay, for the people who don't know, InfluxDB is just a database optimized for time series, okay? So in the MySQL database, we have more sort of like a digital twin of the building. So we have like a database models for every equipment, for every data point, for I don't know, rooms that are there, all that kind of stuff, okay? And in the InfluxDB, that's where we store the sensor data that belongs to those data points and equipments and everything, okay? So we collect data every 10 seconds. We post it to our InfluxDB. And then we have built, of course, a website that also uses that API where you can view the building. It looks like this. I just wanted to show it a bit. And how we implemented this is that on this platform, this is where you configure your AI model. And I want to stress that it's not AI engineers that basically configure these models. It is meant so that building owners and people that don't know anything about AI engineering, but do know how the building works, that they can configure the AI model, sorry. So how does that look? You can select, like when you create, I just click through the model real quick. So you can, the model is called the Weather Impact Predictor. Very nice name, thought of it myself. And you select that, you can select the training data period. You can select how often you want it to retrain. Then you basically select a room, and from that it can infer all the data points that are related to it because of how the database is just structured. Internally, You can review and save it, and then you save it in here. This is basically the admin view for machine learning models that you have for your specific building. So every building that we have, we can create new machine learning models this way. Okay, and here I show a small piece. It's a bit small, but basically what it just says is it gives a bit of information about the status of the AI model. It's like a management system, version management system. So you see the version when it was last trained. You can manually retrain it or select a different version if you want to. And this is then further used. So how does it look like a bit more technical? We have a user on his laptop that configures a model. He saves it. It goes into MySQL. So our MySQL actually saves the configuration of a machine learning model that we want to train. All right? And then either via manual retraining or via some sort of automatic retraining, a Redis message is sent. Okay, so we use Redis for this queue. And then we have implemented our own AI training service. That's just a VPS. I've created it. It's just a Python Docker. It's built on PyTorch Lightning, PyTorch, pandas, numpy, and it's deployed via Docker, and it listens to Redis. So what does it do? It creates, given the configuration, it says like, hey, you need to train a model with this ID, it loads it in. It knows which room to use for it, knows how to resolve the sensor, it creates a data set, it trains a model, it exports it to ONNX, and then uploads it to MinIO. How many of you know what ONNX is? Quite a lot. Okay, for the people who don't know, ONNX is the Open Neural Network Exchange. That's what it stands for. And what you, for example, can do, you can train a model in PyTorch, you can export it to ONNX format, and then, for example, load it in TensorFlow. All right? So it's this sort of open format on how to describe neural networks. You can export it to that format. And we do this because this is built in Python, obviously, right? But we want to use it in other places. And I'm going to come to that later. So that's why we export it to ONNX. And this is the logo of ONNX. And MinIO, that's just blob storage. So this is all in-house, basically. We don't use any Azure services or AWS services, anything. We just built this ourselves because we want to keep it close to ourselves. So this is the AI training service. And then, when the model is trained, we have a background service. And this is one example of how we can use a model after it's trained. But we can use many different ways. I'll explain later. So we have a background service. It loads in the ONNX model. We just upload it. It loads in the weather forecasts. And then it generates predictions and saves them in the database. Makes sense? This runs every hour. Okay? And then, as a final step, with business logic, these predictions get interpreted when requesting set points. So I'm going to request the set points for the next day. It's also going to load in the predictions of the model, so how much impact the weather is going to have, and then I'm going to implement some business logic, which is not, it's a for loop, I think. It's really easy, just adjusting the set points. And how does the result look? It looks a bit like this, right? This is a bit extreme example with a lot of discomfort that's accepted, but you can configure those in our platform that you, for example, say, I only accept 1 degree discomfort, and then it's going to adjust accordingly. And this means that we only have to heat for this part, and all this heating is done by the weather. And this is an extreme case. In general, it's about 3 to 5% savings for every room where it's implemented. All right? While we're at it, we could also do the end-of-day optimization, so we also implemented it because it can use the same model, right? And this is just, we can stop heating a bit because there's often a lot of, the heat goes into the walls and it doesn't feel like it's cold when you stop heating 1 hour before everyone leaves, okay? So these are just small places where we can pick off the energy usage of that room. So to recap this, how does it look? We have this building with the edge device. We have a user with a laptop. They both communicate with our API. We have a MySQL database, InfluxDB, MinIO for the blob storage. Then we have Redis. We have our own AI training service that communicates with those 3 as well. And then we have our background service, which also communicates with those. That's it. All right? So another use case, which wasn't needed for the one that I just explained, but we have another one that calculates optimal set points. How hot does a boiler need to, how much hot water does it need to produce right now? In that case, we want to load a trained ONNX model onto the building itself, because our controls will run locally, because if the internet dies or something, you want the building to continue running. So we run our models locally. What we do is we load the ONNX model from the same database onto the building, and we use it in the control. And here our control software is written in Golang. I don't know how many of you have experience with Golang, but what we did for this is there wasn't really an inference engine for ONNX in Go, so we built our own. It's called GoNNX, very nice. Also came up with the name myself. And it's open source, so if anyone wants to contribute, it's very welcome. And it basically implements the ONNX protocol in Go, so you can run models in Go. So our general implementation cycle of machine learning models looks like this. We think of a new machine learning model type, or actually we think about a new use case, and then the corresponding machine learning model type. We implement how the configuration should look like in the database, and we implement the training procedure in our AI service. And then we implement how it is used. So that can be locally in the building, like I just explained. It can be as a background task, or it can be in the browser. We also load in ONNX models into the browser, and you could do simulations there, for example. Okay? So basically, to recap it, we have one server with one GPU, and we train and use hundreds of small models every year, basically. They retrain themselves weekly. And because these models are small, we can run them on our smart base, which is the edge device, and it's just the Raspberry Pi compute power. But we can run, I think, 100 of them simultaneously, and it just works. We can still use them, which is nice because we don't have to worry about like getting an NVIDIA, what's it called, like I'm forgetting the name, but you have like these edge devices on NVIDIA. We don't need them. We can just use a Raspberry Pi. It's good enough. And accumulated, these models make an impact, and they reduce the carbon footprint of buildings. So, as final words, I won't be training like a next foundation model the upcoming year. I won't train something with 1 billion parameters, but I will train a very small model of 1,000 parameters that will save 2% within a building. And I'm good with that. So, thank you for your attention. And are there any questions?
I already see hands for questions.
Thank you for the talk. I was just wondering, it sounds a little bit like you're solving a reinforcement learning problem because your actions with these HVAC equipment adjust the environment. So how do you train a new model weekly if you're also perturbing or interfering with the climate in that area?
Well, the model, like the use case that I described isn't reinforcement learning because there we are predicting the difference in temperature, and that's a supervised problem because we see the weather does this in 1 hour, and that has the result of this on the room temperature. If we were to control equipment, so saying we want to control this equipment, we're going to regulate how much it should open or close, then you could use reinforcement learning. We have used it as well. But I found that reinforcement learning doesn't work really well in our industry. Why? Because our actions and responses, so the rewards that you get after taking action, are very delayed. So it's like you take an action and then 1/2 hour later you see the result in the room temperature, which means you need like a lot of data, like 20 years of data of a building to really get a good model. And furthermore, every building is different, so you can't really generalize across buildings. You have to make like these specific models for specific equipments, and that just doesn't work that well. So that's why we use supervised learning and just try to move around it.
Okay, thank you.
Yep.
I saw another hand raised downstairs here. Let's see if I can make it alive.
Yes. Thanks. I was wondering how much data do you need to be able to model, let's say, the temperature dynamic of a specific room? Because you have seasonality effects, etc.
Well, like that depends on how. Like we try to solve a use case. So So I'm going to interpret your question as when do you have enough data to make a useful impact on a room, right?
Yeah, that's fair.
I would argue that after a month or 2 months of data, you can start doing this. But you have to retrain it every week because you haven't seen all seasons yet. So That's what I say to the people using the models. I say you have to retrain it. Then we can't just like train on 2 months of data and then never look at it again. But in general, after 2 months of data, this particular use case that I described, then it's good enough to start using it for a model.
All right, thank you.
Any
Nice.
other questions?
There you.
When I saw the title for this presentation, I actually interpreted it as being about something completely different, which is fair. This was also very interesting. But now I'm wondering, so the title mentions CO2. Clearly that's about CO2 reduction, as in reducing our energy usage. I thought it would also be about CO2 build-up from humans in a building. So that brings me to another question. Do you guys deal with that as well? And do your models deal with that as well? And also, do your models keep in mind, for example, you have a meeting room, it's unused until a full group of people comes into that meeting room, and all of them are their own little heaters, so they heat up the room, so you wouldn't want to heat it. Do your models get this advanced, or do they only look at the weather?
So these models don't use it yet. We are very aware of this problem because it is a problem. We have theaters and it's horrible. Basically, to answer your question, CO2 sensors, we don't always have them. So I'm taking the cases where we do have them. For the other ones, you only can do like your best case scenario. If you do have CO2 sensors, I've thought about this a lot because I thought like, can you make some sort of prediction about when people are coming in and everything? But eventually, my opinion is that this comes down to implementing a good schedule within your platform. Because if you have a platform and you say like, hey, I'm having a conference room, you know that in a conference room a lot of people will come, and you see I have like from 8 to 10 people will come there, then you should know that CO2 is getting a big, it's having an impact on it. So we have made models for simulations, and there, when we have it, we always include CO2 because it really has a big influence on the temperature, also in gyms, for example, where people are, and then it really takes up the temperature. So it really makes a difference. But for our modeling, we generally don't use it because it's more like a problem of set points and schedules.
Yeah, clear.
One more question in the front here. I'm just going to give it to you.
Yes. Thank you. So when the weather very suddenly changes, for example in winter, if the degrees go down by 10 or something in a week, you don't know that yet, right? So you have this cold start problem, no pun intended. How do you deal with that?
Can you repeat your question? I missed the first part.
So you retrain on a weekly basis, right? And you start from scratch in a new house.
Yeah.
What if the temperature very suddenly changes in 1 week? Then you're behind for 1 week, right? So you miss a lot of optimization there. Do you do anything to prevent that? Like, do you start your models with a sort of bias towards the seasons, or?
So the best thing we can do is retrain it manually in that case, but this will only happen at the beginning of buildings, at the beginning when you start to come into a building. So, and it is a very valid question indeed when you haven't have data for that weather condition yet. But often what happens is during the first 3 months, there are also a lot of other different problems within a building, just like the boiler doesn't work yet, this equipment doesn't work yet. So a lot of people are hands-on on there. So it's not like the technical answer probably you're hoping for, but this gets solved automatically during the process because there's also a lot of manual work still being done there.
Yeah, see. Thanks.
Right.
I think we have time for one more question. There in the back. Just going to make the run up again.
So thank you. So rather than learning the impact of weather on a room, why don't you try to learn the parameters from that room? For example, the heat loss, the surface area of walls, the R value, the impact of solar radiation on a room. Because then if you have those static variables, then you don't need to retrain the model that often, right? You only need to watch the room for a period of time, and then you can just reuse that information all year round.
Yeah, it is very good. Yeah, we tried. I tried. I haven't got it working yet. It's also because of my lack of physics knowledge a bit, I must say. But it's also what I found is that there are like multiple settings that can lead to the same behavior of a room. So you can have a very small closet that that's like has a really it reacts really fast, and its temperature can increase really fast. But you can also have that in a room with a lot of windows, which is very big with sun on it. So how are you going to like distinguish from only that data? I found it to be not. I haven't found a way to do it yet. But if you have a way, please come talk to me afterwards.
No, I can imagine. I mean, you know a lot of the variables, and it depends how much input data you have for that room, obviously, right? If you don't know the solar input for a room, yeah, it's very hard to confuse with surface area. So yeah, thank you.
Yeah, thanks for the question.
So that was it. Thank you very much, Bram.
Thank you.
Of course, you're also getting the famous eye present. Here you are.
Thank you very
Thank you very much. And for all of you, I think it's a break right now, and coffee break. We start again at 3 o'clock, so get yourself some coffee.